Hello, my name's Tom Chivers, and this is my cousin David Chivers. I'm a science writer, science editor at the magazine Unheard, and David is a professor of economics at Durham University, and together we wrote a book called How to Read Numbers, a guide to statistics in the news and knowing when to trust them. And we decided to write this book about a year ago to help people understand how to use numbers in the news, how to read numbers in the news, and how to understand when they go wrong, when they why they go wrong. And yeah, we're just going to take you through a little bit of the stuff from the book and help you sort of hopefully explain a little bit about what we're trying to do, and to sort of give you a few hints and tips for understanding how numbers are made, how they get into the news, and why they go wrong. Dave, anything you want to add to that?
No, I think that was a great introduction. So let's get started.
All right, cool.
So thank you very much for the Bradford Literature Festival for inviting us. It's a lovely thing to do, to be able to talk about our book, and there you can see it in all its glory. So I guess to start off, I think it's good to read something from the news itself. So this is not headline, but a direct quote from the Daily Telegraph in 2018. And if you give it a read, I'll give you some moments to read it. Can you notice anything wrong with it? Does it make sense to you? Are there maybe some errors in it?
I think I see one, Dave.
Okay. What is it, Tom?
So you see, it says compared with youngster. So children born to older men had 18% higher odds of having seizures compared with youngster with fathers. And I think that should say with youngsters, because it's
yes, you're right. It doesn't make sense, does it, compared with youngster? Obviously, the Daily Telegraph having a bit of a nightmare there. Their copy editing.
That was after I'd left them.
Yeah,
so, it all fell apart.
Youngsters. Now, the question then, though, is there any other errors, or if not errors, is there anything else that's misleading?
Well, and once again, completely unprepared on all of this, obviously. But I think it is worth asking, 18% higher than what?
Yeah, I think that's the thing. And I guess the point of showing this is how quick and good we are at sort of noticing typos. So I said most people who would have read this, perhaps you yourself, would have been able to see at least something was wrong with it. You read it and it just didn't really make sense. So you could tell something was grammatically incorrect. But for those, then I'm not sure how many people would sort of immediately notice this. It's not quite an error, but it's certainly misleading, because I don't know about you, Tom, but it does beg the question, or at least does ask the question rather, what is the probability that you, as a father, or becoming a father, aged 25 to 34 years old, would have a child that experiences seizures? Because if you don't know that, then this information is pretty useless. So in this case, we probably want to ask, what is the absolute risk, as opposed to the relative percentage increase? So at a guess, would you know what this is, Tom?
You know what, actually, honestly, despite the fact that we literally wrote this book, I can't remember very well. It's something, is it like 24 out of 100,000? Is that right?
Wow, that's pretty good. Well remembered. It is 24 out of 100,000. So you did remember that. So if you're a younger father, aged 25 to 34, that's when you become a father. This is the sort of the probability that your child will get or have experienced seizures, and this is sort of what we would call in absolute risk terms. Now, if you remember, the headline was saying an 18% increase for older fathers. So an 18% increase is 28 in 100,000. So for older fathers, that's aged 45 and 54. So I don't know about you, but if I was an older person, like say Tom, for example, and he started to have a, I don't think you're not quite that old yet.
No, I'm not quite that old. No, I'm getting there.
But I was, you were deciding to have another child. If it was sort of given to me this 18% increase, it might affect my decision about whether to have a sort of another child or not. But if I was seeing these sort of numbers, so 24 in 100,000 to 28 in 100,000, I probably would think that's not a big risk. I mean, you might be different, but you can see here the problem.
Yeah.
And I think it's an important problem because obviously the media are trying to present this. I don't necessarily think they were doing it in a sort of underhand way. I just think they probably didn't think in too much detail about it. But you could see how this could affect people's behavior or worry someone. Can you imagine if you're, if a new father's with a pregnant a partner was sort of doing, I think it would cause some amount of worry where, the probably, if you looked at these numbers, it would change. So you can see where the problem lies.
It's worth noting just as well, just to leap in, Dave, that even if you were an older father and had this, were to have a child who then had seizures, it's only actually the difference in the risk is only 4 in 100,000. So this is the change in absolute risk of this 18% thing. It sounds really big and scary, but actually the change in absolute risk is 4 in 100,000. There's a 4 in 100,000 chance that you would have that your child would have seizures that they wouldn't otherwise have had. And when you start looking at the breaking it down like that, it sounds very different to a stark, scary number like 18%.
Yeah, that's a really good point. And I think the reason being is that we are incredibly good at sort of reading. We're very good at reading, except for me. I'm not as good at reading as you are, Tom. You're fantastic. You're a good reader. You notice sort of these things. And I think it's just worth sort of thinking a little bit about this because like 200 years ago, we weren't very good at reading. We were sort of, not many people had access to literature. I mean, we look at the sort of UK data, even though we could probably talk a little bit about this, about how they go about finding literacy rates in different countries. But you can see this sort of sharp upwards trend. And this can only be a good thing. But it does sort of raise the question, why do we think literacy is a good thing? What do you think, Tom?
Well, it's funnily enough, it was because we think it because it's important for people to be able to get involved in democracy. I mean, there are lots of other reasons. Reading is a great joy and a pleasure and brings blah de blah blah de blah. But actually, the really crucial thing from the point of view of Britain, when it in certainly a couple of hundred years ago, was the franchise was expanding. We were giving more people the vote. And there was a sudden realization in about 1850 or 1860 that a large number of people who were about to have the vote couldn't read. And so you literally wouldn't be able to read the newspapers and see whether or not the government of the day was doing well, that sort of thing. And it became starkly obvious to people that to have a functioning democratic state, you needed a literate population who could follow the information that was presented to them in the news. And so that led to a lot of education reform acts. It wasn't the only factor, but there were various reasons. That was one of various factors which led to a push for greater education and literacy in the population.
Yeah. And I think that sort of our argument, at least from the book, is that because we're increasingly seeing this information being presented in non sort of just written form, it's in data or in statistics, we really should be able to read statistics and data at similar levels that we are able to read written word. And we're actually very, very good, as we said, at the written word in general, but we're not quite as good at statistics. And there's a number of reasons we might touch on as we go into that. But I think the question now but people are going to be thinking is how, I'm a bit underconfident with mathematics. Now I'm an economist, so, it's going to be easy for me to say. But I think a lot of people are going to be sort of underconfident with mathematics. So I devised a little sort of thing that I think you should be able to do. And I just wanted to sort of ask you, whether you could work this out. So I'll give you a few moments to do that. Right, that should be enough time. What's the answer, Tom? Tom's gone. He's really gone. He's gone. He's been completely destroyed by the question.
Yeah. So what happened there was I made a bit of a mistake, which was to press enter but the answer, I will tell you, was 47. It was 68.8085106.
Okay, so some people will accuse you of cheating there. Why would you say that isn't?
Well, I didn't cheat. I typed into my browser bar. Like, it's easy. I could have done it on my phone. That would have been actually sensible, because then I wouldn't have pressed enter and taken myself out of the screen. But you don't. Why would you want to? I don't know why you would want to do that in your head. It would take ages. Whereas you're literally carrying a calculator around with you all the time these days. You just do it in 5 seconds. No, you don't need to do that in your head. It's too difficult.
And I entirely agree with you. I think that the idea here is people who think they're underconfident sort of think that people who are good at maths are people like Carol Vorderman, or maybe the younger generation, Rachel Riley on Countdown, and they think, oh, I need to be very fast in my head to be good at mathematics, which is completely bizarre, because you wouldn't really say that just because someone's a good speller, they can be like Shakespeare or something. It's just a very strange argument. It's obviously a facet of mathematics, and it's something we would encourage maybe younger people to learn to develop their skills. But as somebody who's sort of, an older sort of individual who's learned mathematics at school, just use a calculator, because it is more important that we know how to use the tools that are available to us than it is for somehow doing this thing in our head like a sort of computational thing. It's very easy for a computer to do, and we have those tools. In fact, I haven't probably added up in my head for a very long time. I use data every single day, and it's not that important. So I think it is important that we sort of recognize that lots of people feel underconfident about their mathematical skills. And I think partly it's because of this reason that we think, oh, people are going to be better and we have to do it, in very, very quickly, which is just not the case. You don't have to do it quickly at all. I think another reason people might be put off by maths is something like this. Tom, what is this very obscure equation that we see?
It's Bayes' theorem. The probability of A in the event that B equals, and then I get confused. It's a lot of numbers and symbols, or symbols and symbols.
Yeah, so I think, because we know what this means, I know what this means. I can read that pretty well. I understand it. It's actually it seems slightly counterintuitive when you sort of explain Bayes' theorem to people, and you've written about this before. But actually, when we actually write this out, it's not so difficult if you know how to read it. But again, people associate mathematics with complex notation that they don't really understand. So it's a little bit like if you saw this, which is sort of Japanese word. If you're not Japanese, you don't know how to read Japanese, this is going to feel completely alien to you. But I can assure you, it's easy.
It's very clever.
Yeah, because this is Japanese for it's easy. But the idea here is, it's just a notation, and this is not mathematics. So this is the notation, or this obviously this is mathematics, but this isn't, I would say, mathematics itself. It's the notation for it. So the thing we need to start thinking about is, well, what is statistical literacy? Because we've sort of been banging on about it for a little bit. And I think we would argue that it would be something like this. So obviously the pandemic has brought to the floor, this incredible use of statistics and sort of R rates and getting to grips with various difficult things. But it raised questions like this. So, Tom, do you reckon you can explain to everybody what these things are?
Okay, so it should be, we all know now that there's something like 150,000 people have died in Britain from COVID, and it's been disastrous and tragic. But actually, you'd think that would be a fairly straightforward statistic. You've either got a dead body or you haven't. But it's not. It's a lot more complicated than that. There are at least 3 ways, in fact, that are regularly used for when you're talking about how many people have died. There's confirmed deaths, and that is the number of people who died after having a positive test from COVID. That was changed, I think, in June last year to the number of people who died after having within 28 days of having a positive COVID test, because presumably some number of people had a positive COVID test, then got better, then were hit by a bus. And you don't really want to include them in the COVID stats. But then there's excess deaths, which is the number of people who died that year compared to a baseline average taken from the last several years. So you look at the number of people who died in the average January or the average March over the last 5 years and say, if it's more than that, then that is the excess. Or you can do it from 1 year. The various different ways of counting it. Or then there's the other thing, which we haven't mentioned in this, that just the Office for National Statistics provides a number of people who have died in which COVID is mentioned on the death certificate, and that is generally considered the most precise. But none of these, they're all different numbers, and they all provide they're useful for different things. None of them is the right one.
Which one's the correct one, though? Surely there's must be a correct one here.
There is not a correct one. Generally speaking, the confirmed deaths will be an undercount of the will be lower than the other 3. Excess will be higher than the other 3 because it'll take into account things like people who have died of cancer who weren't able to get an appointment during COVID, and then there is the ONS will probably be in the middle and might come closest to the number of people who have died of COVID. So, it really depends what you're trying to measure for, because do we say that the people who died of cancer during the COVID epidemic because they couldn't get an appointment don't count? Then if you're interested in that, then you're interested in that. If you're interested in the number of people who died of COVID, then you're interested in that. It's different. There are different things to use for different purposes.
And I think that's the point, really. So again, people associating mathematics with, say, just the right answer, it's not really debatable. Here you can see there's a big debate. What should we use? And I think, again, people sort of thinking that, say statistics is a very dry subject would be sort of slightly maybe intrigued almost to say, well, no, this is part of it. But in order to have these conversations, we need to have a level of statistical knowledge for us to really talk about it. I think that's the point. And I think that's what statistical literacy really is. And these are sort of things to me that interest me. This is statistics in my mind. It's not notation, and it's certainly not doing it in your head. So now we've sort of convinced everybody that you can be very confident about your sort of mathematical abilities. We probably should sort of see where the news maybe goes wrong a little bit. So this is a Guardian headline: "Strong language, swearing makes you stronger, psychologists confirm." Do you want to talk a little bit about this? What maybe?
Yeah, sure. So I mean, it was a study from about 2017, and they looked at a small group of people, and they made them first lift weights and shout something, but not a swear word, and then they did it again and made them lift weights and shout a swear word, and they saw whether or not people on average lifted it, were able to lift more weights when they were swearing than when they weren't, and they found, in essence, that they were. It was a group of about 50 people in one version of the study, and about exactly 29 people in a different version of the study.
So, but surely it's an academic study, though, so there wouldn't be anything wrong with statistics. It's published paper, it'll be peer reviewed and everything. So
right. Of course, completely unimpeachable, and it's definitely true, and people swear. No. So, just on the face of it, we should be a bit wary of this idea, because if it really makes a really big difference that swearing makes you load stronger, it makes a real difference you can actually detect, then the Olympic weightlifting final would be not broadcastable at all. You just couldn't show it on telly, because they would have worked that out, and there'll be lots of people swearing all the time. Now, it may be there's some small difference, and you have to do some sort of statistical detection of it. But when you're looking at a small number of people like this, a small sample size, what you might just have happen is that they randomly happen to do better in one set than in the other. And when you're looking at small, like if you were to roll a dice a small number of times, you might happen to get a 6, or if you flipped a coin 5 times, you might only get 5 heads. But if you flipped a coin 100,000 times, you would get about 50,000 heads.
And I think this is interesting, because I think the difficulty, I think people probably, if they know something, that should be slightly wary of small sample sizes. But I think we should probably see why that is, what the whole, why there's a problem with small sample sizes. And I think the idea, first of all, is to think about, well, what is a sample in itself? So when we have a sample, we're interested in a sort of the population. So it could be the population of the UK, it could be the population of the human race. It doesn't really matter. And what we're trying to do is take a piece of that that's representative, as if you were walking down the street and you went past a bakery and you smelled this lovely bread, but then you saw that people were offering a nice piece of the sourdough beforehand. That piece of sourdough should be representative of the loaf inside. Then that's the point of a sample. It needs to be representative, because if it's not, then it's not really a very good sample. So the reason why we need let's think about distribution and what it looks like. So this is the normal distribution, a very sort of famous sort of thing in statistics, and you can see it looks sort of this hump shape. Some people call it the bell curve. And basically, this is just a simple one for height. So we'd imagine this is what the population would look like. We have most people around average height. I'm about average height. And most people are going to be around where sort of my height is. And we'll have a fewer people in the sort of population who are very short, and some people who are very, very tall. And this is what we really should be aiming for if we're going to sort of sample people. for height, we'd want our sample to look like this, to actually look like this distribution of people. And what's amazing about this sort of statistics and this property of statistics is we don't need to sample the whole world. We don't need to ask everybody's height in the world to get an extremely accurate picture of what it would look like. We just need a significant amount of people, a significant number of people. The question is, how many do we need? And that's a tricky question to answer. But I think we said that, if some sample is probably between less than 100 people or 100 things in that sample, we would be slightly worried.
Yeah, I mean, it's totally arbitrary, but and different populations you're trying to sample and different effects. That if you're looking for a more subtle effect, you need a bigger sample and all this sort of stuff. But as our completely arbitrary rule of thumb, we went into the thing saying, look, if you read a study and it has a sample size of less than 100, then just be a bit more wary. Go and check it out a bit.
But it's not to say that it's necessarily wrong. It could be interesting that this could be a further thing to look at. It might be quite a big effect size, and we might sort of do the study again and with a larger sample. It just means it's probably not concrete because we don't have this nice shape in our sample. And just to sort of go into a little bit more detail of this is that when we think about the variance, which you might have done before at school if you haven't done some mathematics, the sort of a lower variance means that everyone's clustered around the average. So if in height, everybody around the same height, and a higher variance means that sort of data is a bit more variable, if you will. It's going to sort of squash that curve because we would expect then more tall people in the population and more short people in the population. So that's how it works. But I think this is quite hard conceptually to think about, really, because we don't have any data with us. So what we sort of said, well, why don't we give some example? And I don't know if you've ever played the game Craps, Tom.
I haven't, but
I haven't actually either. But this is game Craps. But can you explain it to me, maybe?
Yeah, I mean, it's a dice. It's a dice only insofar as it's a dice game where you roll 2 dice, and the score that you get on those dice matters. And getting a 7 is either good or bad in some way. I forget. You'd have to.
I can't remember either.
Yeah. Anyway, but if you roll 2 dice, you are much more likely to get a 7 than you are any other dice. There are 6 different ways to get a 7, and there are 5 different ways to get a 6 or an 8, and there's only one way to get a 2 or a 12. So if you roll the dice hundreds and hundreds of times, you will end up seeing a hump in the graph, very much like this, or very much like the normal distribution, and because that is just the way the probability rolls out.
Yeah, and I think so I've got 2 dice here, like in the sort of teaching way. I've got the actual experiment, so black and a purple one. I think from a D&D set or something, which is very good. Encourage people to play sort of tabletop games for statistics is a good way of learning. But basically, the idea here is if we then have a small sample size, we're reliant on whatever comes our way. So I'm just gonna I'll do this to roll them in our thing and say, well, what's the first bit in our sample? And I actually got an 8. So you probably can't see that, but I got an 8 here. And so the chances of me getting an 8 is quite high, really. It's in the average. It's not completely arbitrary. It's not sort of like we've got a 12 or a 2. So I'll do it again, just quickly. I got a 6 again. It's sort of around the average. It's quite likely. And I'll do it again, and I got a 5. So again, not too likely. But the question is it likely that just by me doing this, I'll end up getting snake eyes, like a double 1? And it is quite likely that I'll get that because it's 1 in 36. The problem is if we only do it, say, 36 times, if we can do this, we can see that it won't actually look like this. It'd be very unlikely that we get exactly 1 snake eyes, 136, exactly 2 out of 36 rolls will be 3, etc., etc. It won't look perfect. And the reason being is it's just this idea of statistics is that the more we do this, the more it's going to look like this shape, this sort of nice, almost like a normal distribution shape. And it's sort of an interesting property of statistics that it will look more like that. And so if we have a small sample size, there is the probability that we just get these sort of extreme results that we wouldn't usually have, and it wouldn't look like a representative sample. So if you really want to do this and prove it to yourself, as in you just think statistics might be made up, by all means get 2 dice and keep rolling them for different times and plot them out, and you'll be able to see as you go that it'll get closer and closer to this, and you'll be more able to predict with certainty what the distribution is going to be. So basically, this is the idea of sort of sample sizes and why they're important. But does having a large sample size mean everything is okay? And this is a question that we get from the headline, Brits like it cheesy, cheese on toast is being voted the nation's favorite snack. And this had 2,000 participants in it. So it must be okay. Tom, what do you think?
Yeah, obviously fine, completely fine. Next question. Sorry, yeah. So no. So this study was, well, it wasn't a study. It was carried out by some online firm called Raisin.co.uk, who were advertising something or other that now escapes me. But they went and they did an online. They took a sample of people who online by literally asking them, you know, what's your favorite snack? And of course, that is not a carefully weighted, carefully random sample of the population. It is just the people who happen to be on their website and click on their website and then agree to do this particular survey. So it is not necessarily representative.
It's a large sample. What should be wrong with that?
Well, I mean, for instance, let's imagine. Well, okay, so let's imagine that we were talking about height in the last thing. Let's say you're trying to do sample of Britain's population, and so you set up a stall in a road somewhere, and you measure the heights of people as they walk past. And assuming that you're in a city that's, you know, reasonably representative of the country at large, you probably get a reasonably representative sample. But then one day you're doing it and you set up your stall outside a basketball players convention, and suddenly you get a bunch of like 7'3" people walking past, and you're dutifully measuring them down, and then you go back to your masters and you say, well, I've been doing the maths, and it looks like the average person in Britain is 6'8", and that's not right, you know, because it's not because you got your sample wasn't big enough. It's because your sample was biased. It was not representative of, you know, and you could have taken as big a sample as you like, and it would have just made you more and more confident about your wrong answer. And I don't know what Raisin.co.uk did with this, but I don't imagine they very carefully went through the phone book and then reweighted for the different ways it could go wrong. I think they probably just took the first 2,000 people to fill in their form online, and we have no way of knowing whether the sort of person who fills out a form online on Raisin's website is representative, if it has the same sort of snack preferences on average as the population at large. Maybe they are just happen to be a bunch of cheese fanatics for whatever reason. So we don't know. This does not tell us almost anything at all really about the preferences, the snack preferences of the wider British population. It tells us quite a lot about these 2,000 people, but not much more than that.
Yeah, and exactly. But it's interesting you mentioned bias there, because we're well used to sort of political bias. We think of that in that way, but it's not quite political bias, is it? I mean, it could be sort of if you're a social democrat, you're a huge fan of Twixes or something. But it's probably more likely that we think about biases. It's that not representative idea. We want that distribution. So you think back to that normal distribution. We want that distribution to be a sample of the population. Having a large one is a sort of usually a good thing to make it representative, but having a bias in there somehow, whether it's surveying people online or even the time of day you ask, all of these things may not make a representation of the population we're interested in. So we need a large sample and we need a non-biased sample.
It's as though sorry, carry on. I was just going to say one way I was told to think about it. Oh God, this is dreadful. I'm going to stop. You carry on.
Okay, I was going to say the one place to see it obviously is on Twitter, but you can say your bit now.
It's just it'll be fine. I was going to say one way I used to think about it is if you imagine you're drawing balls out of a barrel, and you draw out 10 balls, and some of them are red and some of them are white, and you have to work out what the percentage of the barrel is made of it. And that if the more you draw out, the better your sample will be in theory. But if it happened to be that red balls were lighter than white balls, then you would preferentially be drawing more red balls out, and you'd be as you get out more, you'd be thinking, oh God, there's all red balls in this thing. But actually, your sample would be biased because you'd be drawing them from near the top. But we've now moved on, so let us go on to this Twitter thing.
Okay, yeah, that's good. Well, whatever works for you, Tom, in terms of how you sample it. So this is a tweet by somebody, and they were very concerned that the only sort of polling results that were sort of quoted on BBC and ITV were YouGov, and this was for a debate between Boris Johnson and Jeremy Corbyn in the 2019 election debate. As you can see here, all the other sort of places, the Times, Martin Lewis, had very large sample sizes. They had sort of 8,000, 23,000, and YouGov had a sort of very a lot smaller one at 1,646, but was seeing a sort of more even sort of debate here. So interestingly, they were accusing, I guess, the BBC and ITV of bias here, but why would the YouGov sample be better? Well, I guess the reason is YouGov will weight the chance of encountering somebody. So let's say in your sample you had a larger proportion of men than women in your sample for whatever reason. We know in the population roughly how many men and women there are. We can sort of apply a weight to them to sort of correct for that bias. So this is what YouGov will do. The others will probably just take the raw numbers, which is why you get a more accurate one. And it's also why if you just retweet on Twitter and so it'll say, retweet for a large sample size, it's not going to make your sample more representative just because it has a larger sample. So, yeah.
I mean, it's worth remembering Twitter in particular is as Dave was saying, there was a lot of people were very upset. All these Twitter polls showed that Corbyn had won this debate, but the only the proper poll by the YouGov showed basically a tie: Johnson 51, Corbyn 49, and and people got really upset about this. But this is because Twitter is not the population. Twitter is people who are on Twitter are generally younger. They're generally more educated. They are generally more left wing, and people who are younger, more educated, and left wing were more likely to vote Labour in the general election. So the sample was just not representative. It was not randomly sampling people in the population. It was not carefully applying sort of statistical weights to try and get the best. It was asking a bunch of young left-wing people whether they would vote Labour, and of course a large number of them would. So it was not a representative sample.
And what's interesting, though, is, I mean, just the other day, we've seen the media seem to like reporting on things like either Twitter polls or, non-representative samples, like self-selecting samples. Like I think there was a sample from the Express. So it was Express readers. So we can say, as I said, we can say something. And, right before, we know it's the people. This is the views of the people that answered that poll, and we might be able to say something about them. But what we can't do is then extrapolate it to the rest of a general population that we're interesting. That's the most important thing here, I think. So let's move on to this headline from the Daily Telegraph. Men eat more food when they are trying to impress women, study finds. What's all this about, Tom?
Okay, so poor old journalists, right? They with the last few things we've been talking about is journalists reporting on things that perhaps were the study. Well, certainly in the case of the raisin thing, that the study wasn't that great, wasn't even a study. And the other one, it's a small sample size, and maybe the journalist should have been a bit more alert to that. Although it's hard. But in this case, it was a peer-reviewed, really well-reported study by a famous psychologist. It was very. Apparently very well conducted and everything was great, but it was complete garbage. And the reason it was garbage was not the journalist's fault. The problem was upstream with them, and the problem was that it's a huge problem in science, which is that scientists have to try and get their studies published, and they will do and the only way they can do that is if they can find results that sound exciting. And one of the things they try and do, for instance, is you have to get a certain level of a thing called statistical significance, which is.
Let's stop there maybe and explain what statistical significance is. Which is
right. Okay. It is a tricky thing to do. It is an extremely tricky thing to do. So,
how about this?
Yeah, statistical significance is the likelihood if the likelihood of seeing a result if there was no effect whatsoever. So imagine we talked about the dice earlier on. Okay, this is probably the easiest way of thinking about it. Say you were interested in whether or not your dice were loaded. You're like, well, I don't trust this guy I'm playing dice with, so I want to roll my dice and roll the dice before he used to play and see if he's faking me out by using loaded dice that will always roll sixes. And you roll two dice and they come up both sixes, and you think, well, that's a bad sign. But you don't know off the top of your, you don't know. Sometimes dice roll sixes. About one time in six, in fact, a dice rolls a six. So you don't know from doing it whether those two sixes is just a fluke or whether it is actually because of the dice are loaded. You roll them again and they're two sixes again. Well, you still don't know because sometimes I play Warhammer because I'm a nerd, and I've rolled a lot of groups of 4/6s and things like that, on more often ones. But anyway, so what statistical significance talked about is, although is the p-value is what we should be doing, is the likelihood of seeing that result if there was no effect. So if the dice weren't loaded, how likely is it you'll see 4/6s? And it's, in that case, it's 1 in 6 times 1 in 6 times 1 in 6 times 1 in 6, which I can't bother to work out in my head at the moment. But is about 1 in 200, I think. No, about 1 in 1,000, something like that. In the event that there is simply no effect whatsoever, and it's just a fluke, how likely is it? And it's that. So, and in science, there's this completely arbitrary convention, which is that if the p-value is less than 0.05, that is less than 1 time in 20, then if you see it on a without any effect, you see it less than 1 time in 20, then you can call it statistically significant, and there's a good chance you'll get it published in a journal somewhere.
Yeah.
Now
that's very well explained.
Yes.
So if I just
sorry. Yeah.
What's it all about? I mean, that's the thing. So what is this beautiful? I guess the idea is, I think many people are surprised. This is how a lot of science works, right? Because I guess when you think about proof and various things, when you were at school, you probably sort of say, oh, we, used a Bunsen burner, or we put something in, a solution and it turned the color, and that's the proof. But in data, at least, we don't have that, because as Tom was saying, there's always that random chance that it just occurred by accident. It's not necessarily effect size. So in our book, we were sort of suggesting, well, how would we go about proving that our book somehow made people smarter, or better at statistics? And we were saying, well, how could we sort of prove that? Maybe it's just a fluke if we did a test afterwards for book readers and non-book readers, that they just, the book readers randomly just did better that day for whatever reason. It's just a random occurrence. So in order to prove that, we need some sort of test. And this is what the p-value basically does. It sort of helps us achieve that test. And I think Tom explained that pretty well. Did you want to add anything to that?
I mean, yeah, just the no, I forgot what I was going to say. Carry on.
I'm sorry.
That's right.
But yeah, basically, we have this test, and the thing is, what's interesting, and it is quite a hard thing to grasp. It's not easy, and many academics aren't particularly great at it either. And one of the problems with this test, it does rely on something, which is honesty. If you carry on repeating this test and changing it slightly, it actually reduces it increases the probability that you will get something by random chance.
This is what I was going to say, and I will jump in now. Now. That's exactly what I was going to say. It was that if say you rolled those 4 dice and you got 4/6s, or someone said to you, I've rolled these 4 dice and got 4/6s, I think it is therefore quite likely that these dice are loaded, you would be presumably impressed. But if you had found out that they had secretly rolled the dice 10,000 times beforehand and not told you when they've rolled a 3, a 2, a 5, and a 1, or whatever, hundreds and hundreds of times, and then the only time they've rolled 4/6s, they then pop up and say, I've got this result, it's really interesting, I think these dice are loaded, better accuse that guy of cheating. You would presumably not be impressed. And so if someone is doing these studies, for example, like on book, if we had given interviewed 1,000 people who'd read our book and 1,000 people who hadn't read our book and checked how good they were at statistics, and found that the book readers had done slightly better, we would say, look, obviously the book improves your ability at statistics. But if we'd simply not told you that we'd actually done that exact experiment 200,000 times and disregarded all the times where the non-book readers had done better, or they'd done exactly the same, then you would say, well, you are cheating. And that is called p-hacking. That is when you are hacking away at the numbers to make the probability value look more exciting than it is, and so you can achieve statistical significance, and then you can get it published in a journal. And that that was exactly what was happening with that food study.
But why do academics do this? I mean, that's the thing. So why would they do this? Why would they cheat and lie and do these?
Because you're all scum.
Yeah.
No, sorry. No, because of no, that's really unfair, and it's because of the incentive structure in scientific publishing, which is that scientists' careers rely on publishing research. Journals which publish the research have an arbitrary thing where you can't publish your not all of them to their in their defense, but a lot of them they won't publish studies that don't find a result, and they won't publish things that don't find a result significant to p equals 0.05 or some other arbitrary threshold. And so as a scientist, you do some exciting research into whether jelly babies cause flatulence or whatever, and then you do hundreds of so you do a study and you find it's only at p equals 0.53. So well, better do it again to sure get it under significance this time. And you keep doing it until you get under it. Then you get it published, and that will then your study will be in the scientific literature, and all the ones you did where you didn't find anything to statistical significance will be excised from the scientific literature, and it will warp the literature to make things look like they're more exciting than they are. And that is a structural problem in science, which is a genuine problem and causes all sorts of we could go into that for another hour lecture very easily.
Yeah, and so going back to the headline, basically, this many more food when they are trying to impress women was essentially p-hacked, and we know this because the guy basically admitted to it
by accident,
email or by accident, and it was
a blog post.
But let's move on. So we see a lot of these things. So this is sort of one of the things that people think about when they think stats and news, I think. So especially a glass of red wine. Is it good or bad for you? So this is from the Daily Mail in 2016. Even one glass of wine a day raises the risk of cancer. 2017, next time around, a glass of red is not good for the heart. Oh, okay. So scientists now debunked the myth that drinking moderation. But now it says one glass of antioxidant rich red wine a day slashes men's wrists, and now it's maybe good for your health. And drinking a small glass of red wine a day could help avoid. So it's now sort of changed and flipped around. What's going on with red wine? Is it good or bad for you, Tom? Yes or no?
Oh, it's dreadful, isn't it? It changes every week. So what's happening is that there is a real effect of wine or alcohol in general on our health. The best guess is that it is a slight protective effect at very moderate drinking levels, and then becomes a somewhat more negative effect at rather higher levels. If you're drinking more, sort of 5 or 6 drinks a day or something like that, it becomes negative for your health. But each study is done. We talked about small sample sizes earlier on. When each study is done, and it is you can think of it as a small sample taken of the reality. And sometimes that sample won't be exactly on the line. It won't be precisely where the reality is. So it might fall a bit to one side. Might make the health risks look bigger than they are. It might make the health risks look smaller than they are. So it looks like it's protective. And you like the normal distribution again we talked about a minute ago, it'll scatter around the central point somewhere. And when you're looking at the scientific literature as a whole, you can see that distribution around the true result, and that is good and healthy and normal. But if you report on every single individual study, they scatter around all over the place. So one week a study might come out that finds that that finds slightly wrongly that it's more protective than it is, or one finds that it is more harmful than it really is. And if you ignore the body of literature that already exists and just report on each new study, you can come up with these headlines that say, this week it's good, this week it's bad, this week it's good, this week it's bad. And that is exactly what's going on.
Yeah, and I think this is sort of a misunderstanding of science in itself and how we think of progress. I guess there's this idea of discovery, a bit like sort of discovering antibiotics or something is like, a eureka moment, and then the whole field changes. And this isn't really how science works. It's not this, very rarely you have this sort of moment which is like, wow, this is completely changes. It's a building up of evidence over time. And so the question really we should be asking is it representative of the literature as a whole? So one new study in itself might actually be one reason why it's published is because it's surprising. It could go against that sort of thing. So we need to put it in the context of literature as a whole. I think as well, what's difficult with the red wine per se is that if you notice what was interesting about all of these different bits on health is that they were all actually different things. They were all looking like one was looking at Alzheimer's. I think maybe one was cataracts, so maybe that's a different one. There's lots of different types of things. So if you associate that then with health, it's very difficult because I might not necessarily care specifically about diabetes or cataracts. I care about my overall health. And that's a different matter. So when we're thinking about, I think from a more general perspective about how we treat alcohol and health rather than sort of red wine specifically, we need to sort of put it into sort of a larger context here. So what this sort of graph shows is interesting. Now, can you spot anything that maybe raises red flags for you, Tom?
Ah, yes, I can. Look, there's a word we used earlier, relative risk, over on the left-hand side.
So let's sort of, I think, because again, this sort of, well, I don't know, we can talk about it a little bit, but we don't really know what this relative risk is doing. It's what it was presented in, but I can tell you what the sort of baseline risk is. So the first thing is standard daily drink. So I think it's about 1.25 units. So that's about half a pint, I guess, or a small glass of red wine. And this is your standard daily drinks a day. And then on the sort of the sort of y-axis or the vertical axis, this is sort of the relative risk. And this sort of it's a relative risk of a disease or an alcohol-related disease. So 0 would be a baseline risk of when people don't actually drink at all, and they're still going to potentially get this alcohol-related disease. If you don't drink, it's not like you're not going to be completely immune from getting sort of liver cancer or something, but it seems like you're going to be far better protected. Now, Tom was saying before, which is interesting, that there seems to be this protective effect of alcohol and red wine. And I think one of the reasons the studies were showing that before is an interesting problem, actually. And I think the general consensus now is that previous studies were saying that didn't take into account that people who don't drink maybe have some inbuilt health problems, which is why they don't drink. So then they may be more unhealthy in itself. So it seems like there's a protective effect from alcohol, when in reality there's probably not. I don't,
we can have a row about this afterwards. I seem to remember that. Yeah, I seem, well, certainly had a few conversations with statisticians who think that there probably is a mild protective effect, but we could derail this entire thing. Yeah, so let's not do that.
We can do that. We can derail this a little bit, but there's a debate there anyway. But if you can see, even if there is a protective effect on this sort of idea of sort of relative risk, that as we go up, there's a sort of fan, which is uncertainty interval, and this is sort of the accumulated risk as you're going up. So it's not only that it increases in relative risk. So if you start drinking about 8 sort of units, so 8 standard daily drinks a day, you can see it sort of doubles your relative risk, but it also increases that uncertainty. So we're not sure. So it could be anywhere, from at the very end scale, sort of 450% to sort of just a 200% increase. So it's a bit more uncertain then in terms of the effects that we can see. But the original baseline from the study, just so if you're interested, it would be 914 in 100,000 individuals, that's age 15 from 95-year-old, would develop a condition in 1 year if they did not drink at all. And so if you were going to sort of increase this to 1 standard drink a day, this would be 918 people in 100,000 who drank 1 alcoholic drink a day would develop some alcohol. So it would only be sort of an increase of about 4 people in 100,000. But I think we were discussing this a bit before, it was a bit off topic, is what this means for you and as an individual perspective, and sort of what this means for a public health perspective. But we need to be able to understand these numbers and statistics to have a sort of reasonable debate around this, and how, what alcohol policy should we pursue on this? Now, presumably different questions for different reasons. Obviously people enjoy drinking alcohol, but we can see at a level, even these small changes, this is sort of when we get to 5 drinks a day, this changes from 914 to 1,252 people in 100,000. And, for your own personal risk, that might not be such a big deal and you might enjoy drinking, but from a public health perspective, that could be quite a lot. So these are the type of things we need to understand to have an informed debate. And we're not really going to get them from sort of random clustered sort of bits in newspapers that sort of seem to drip feed up through us over time. Anything else you want to add there, Tom?
Well, just that the position, the argument about whether there's a protective effect of alcohol will rage on for a bit longer. But the broadly speaking, the shape, the idea that there is a moderate but slow increase, it hasn't really changed. The position on what the risks of alcohol are haven't changed for years and years. Each new study adds a little bit of extra detail, but there's been no major changes as far. Certainly, I was writing in 2016. about studies like this coming out saying, "Gosh, new exciting study," and it's probably kind of been saying the same thing for 20 years.
And presumably, even if there was a protective effect, it's not hugely large.
No, it's tiny. It's tiny. Yeah. And it is very moderate. It's in the 1 drink a day.
Yeah.
Sort of level, or less than a couple of glasses of wine a week sort of level. So yeah, it is not. I can go and neck a bottle of wine every night, and that'll.
Yeah, I think that's the difficulty, and it's something when it's very difficult when you see there's a protective effect. There's a protective effect at a small level, so it could also induce people to say, "Oh, I'm going to drink lots and lots of alcohol because it's protective for me."
Exactly. But I also do. You also want to be, as a good economist, these are people's preferences, right? To some degree, like if people enjoy, I don't want to go out and say, "Well, you should be thinking." The only thing that matters is extending your life by another 3 months. If you're enjoying drinking and you're not, I don't want to get too like Puritan about it either. So anyway,
and we are. From a personal perspective of how I do it, I like me. I really like wine. I love it. It's one of my hobbies. But it's sort of, I think, at least from a sort of from an ethical perspective, that we should show this to people. We make them understand the data. And then they can make the risk. So it could be I'm on the margin and I sort of think, well, you know what, I can see those risks and it's not great, but I'm quite happy with where I am. I think it's okay. There's other things in my life, because it's not just risk. It could be also things like family and things, how it affects other things, or weight, lots of different aspects of that. But it could be that say, well, I think I'd be kind of marginally happier if I didn't drink that much, and I will do that. And I think that's the point, is that from at least how I feel, at least, that we should be able to present this to people and they can make their own decisions to an extent. And we can also have a debate about how we do this from a public health perspective. But as I said, we are not really getting that from the media, and even things like campaigns, which are, lots of things like arbitrary units, like 14 units a week. It doesn't show us this sort of gradual increase. There's no. It may actually, when we talk about things like 14 units, and obviously it's for different countries, people think there's a scale off. There's a huge increase of risk if you have 15 or 16, so you're terrified at the 14 level. Or people will think that 14 is absolutely magical and fine, and there's no effects of alcohol from that level, when there obviously is, even if it's sort of relatively small. Let's move on. Anyway, so what about this, Tom? India overtakes Britain as the world's 6th largest economy. What can we sort of glean from this?
Well, it sounds like a pretty big deal, doesn't it? Britain's slumped down the rankings, and I'm doing it again. No, so the thing is that rankings, to the point we tried to make in this book, it is, they conceal an awful lot of information. One of the examples we used in the book actually was that. Let me see if I can get my years right. In 2018, 2019, Man City won the Premier League and Liverpool came second. And in 2019, 2020, Liverpool won the Premier League and Man City came second. And, just with those stark rankings, it sounds like it was the two we did roughly equally well. Mm-hmm. But then when you look at the numbers in 2018-19, Man City won by 1 point. And I think if in 2019-2020, Liverpool won by 18 points or something like that. The simple fact of the simple first and second ranking doesn't tell you how much they won by. There was a big difference in those two things.
So it does suggest that they're the sort of the better team, really. But there is a new data point, because isn't something happening this year that's slightly different? I don't know. I haven't been paying attention. That's certainly nothing important, I'm sure. But so with India overtaking Britain, it sounds like there's been some big change, but actually. India and Britain's economies are of almost exactly the same size. I believe, and I haven't got the numbers in front of me, that that's brilliant. Thank you, Dave. Yes, that's genuinely really well organised. The Indian economy is something like 1% bigger. I can't bother to do those numbers off the top of my head. 1 or 2% bigger than the United Kingdom one. Yep. They are both very comparable as a share of the world economy. They are pretty much the same size, and same with France. And like literally a measurement error could change the position of these things. And there are the various ways that the World Bank, the IMF, and someone else all do these things. And you look on Wikipedia, and they will sometimes have them in different orders because they've measured them slightly differently. It basically makes no difference to anything. And if you then compare that to Germany, which is genuinely quite a lot larger, about 25% bigger again than India's or Britain's, then that is quite a lot different. But that's only one space ahead, just as India is one space ahead of the United Kingdom. And then you go higher again to Japan, which is practically twice the size of the UK is. And then things like China and the US are just in a different playing field. And
putting these things into a rank of 1 to 6 or 1 to 7. It doesn't really tell you anything about how big or how rich these countries actually are.
Mm. And I think this is sort of highlights a really important point, and that's basically, if we were to take just from this headline that Britain is a good job I'm not running for a politician or something. Britain is a world's 6th largest economy. We can say something about this because we kind of have a rough idea how many countries there are. So if we were to say Britain is a relatively rich country from this, well, in terms of the ranking, if we were to do it this way, we can glean some information if we know maybe a bit more about how it was done in terms of what sort of measurement it was in. What we can't know really is something like, or we can't infer from that how close it is. So if we were to think, oh, well, that means because there's so many countries, the UK could be quite close to the US in terms of size, that would be a wrong inference. And I think the thing it highlights is that there's not really such a thing, with a sort of caveats here, as a bad statistic. It's more how we interpret the statistic. And I think that's the important thing. We can get information and we can use that information as long as we're interpreting it okay, even with biased samples, like we said before, then that's all right. The point is how we interpret and how we use that sort of data. So I think rankings can be useful, but we need to know how they're made and we need to know the sort of stuff behind them as well, because these relative positions might be useful for asking different questions, but it wouldn't be so useful if we were to say, look, how rich in terms of GDP absolutely is the United Kingdom compared to other countries. It would be misleading in that case. So I personally dislike rankings in a lot of ways because there's lots of rankings, and this one is fairly clear. You can see GDP US millions, whereas if you saw, I don't know, something like we saw the university ranking tables, there's lots of different ways how people, how they are calculated, and they can all be very complicated and not particularly clear, and things change all the time, and people celebrate these losses or wins and say, oh, look, we're obviously doing something better, and it can be totally random. And the thing is, people can actually have policies built on them. They can say, oh, look, we've fallen down the rankings in some education sort of table, and it could be everybody in the world is getting better, which surely is a good thing, and we don't need to sort of bang heads together and say what's going on with the relative rankings here. And it's a huge problem, and we need to be able to read these things, or else we're obviously going to make bad policies and bad mistakes and decisions. So let's sort of maybe finish off now with also the last headline, which obviously this is going to be part of a wider festival, which is happening online. And there may be some, I don't know, but I've definitely heard this before. People will ask, well, how did you write this most successful book? And obviously, Thomas, your second book now. Tell us the secret road to writing a bestseller.
Well, if I knew it, I would be much richer than I am. But yeah. So this was a story in the BBC, obviously, a few years ago, and it looked at. Now there were 3 different stories we wrote about this, and I forget exactly, but it looked at it analysed books and said, look, if you look at J.K. Rowling's books and whatever it was who wrote Twilight, Stephanie Meyer's books, and her who did 50 Shades of Grey, and we can pull out these particular facts about the way they're written and the sort of words they use in the headline, and the fact that they're written by women who have slightly androgynous names, like names you can't tell whether, so like JK or whatever like that. So, and these facts we draw out from these facts that there is some commonality to them all, and therefore these are what you need to do to write a bestseller. And I mean, my immediate instinct, which is a little unfair, was if you've got some secret code to writing a bestseller, why don't you write something, see if you and churn out a few bestsellers before you release it on the market. But fundamentally, it didn't really make any sense. Shall I explain why, or do you want to go into that?
I think it's a little bit like saying how to become a best-selling author by sort of best-selling author. It's sort of, this type of personal experience, using your personal experience, is saying, well, look, this is how I did it, and you think there must be some secret code in this, where I think that's the thing, is that you want to listen to it. When we want to listen to these sort of very successful people talking about how they did it, and this is how I did it, so therefore it must work for you. But there is a a statistical problem that sort of underlying this, and it's reflected extremely well. And you might have seen the meme on Twitter, but maybe it's just the sort of circles that Tom and I hang out with that would post this. And it is this. And can you explain why we've got this picture of a Spitfire?
It's Spitfire. God damn it! It's got 2 engines. Jesus. Sorry. Genuinely annoyed by that.
Way to wind up Tom. Just in the future, just get something wrong about warplanes. It's great.
Oh, jeez. Okay. So this. I mean, this is a generic 2-engine bomber from the Second World War. I think it's probably something like, in the Second World War, the American Navy noticed that their planes were getting shot at a lot, which isn't what you want. And they noticed, and they asked someone to do an analysis of where to put armor on the planes to protect them when they came back. And they noticed that the planes that were landing tended to have bullet holes in the wings and fuselage. And they said, okay, so they're being shot in the wings and fuselage. That is, so let's put armor on the wings and fuselage to stop them from being hit there again. Okay. And this statistician, whose name annoyingly escapes me now, said, well, wait, you're missing something out here. You're looking at the planes that have landed, and the planes that didn't get hit in the fuselage and wings, the planes that got hit in the cockpit or that got hit in the engines just didn't land at all. All right? They didn't make it back. So, what you actually need to do, the fact that you're not seeing bullet holes in the engines, not seeing bullet holes beneath the cockpit, that implies that what you should be doing is armoring the engines and the cockpit. That's what'll protect you. This is, and that is what survivorship bias. When your sample is it's a form of sampling bias, very caused by the specific thing of the ones that make it through some filter or other are the only ones you're looking at, and in this case it was planes, but in things like the How to Write a Bestseller, there were various other examples of the secrets of how to run a Fortune 500 company or whatever. And what they're doing is looking at the companies that happen to be doing well at that particular point and say, look, these have these these particular attributes which I think are great, so do them. What they didn't do was look at the companies that didn't do well and see whether they also had those attributes. It's a bit like saying, well, look, all these people who got cancer drank water, therefore water causes cancer. You can't. That sounds ridiculous, but it's the same thing. What you need to do is look at the population of people who didn't get cancer and see whether they drank the same amount of water, and you'll probably find that they did. Sorry, Dave, you're about to jump in there.
No, I think it's exactly right. I think this also, people are going to be slightly skeptical. It's not that you can't learn anything from sort of these successful people, but when you do that, you need to say, well, was that the thing that made them successful? And how do we know that particular thing made them successful? And we're not going to know just by the fact that those two things are correlated at the end, as Tom was sort of explaining there. And I think it's just extremely important that we realize, and I think it highlights the point that when we interpret and we see these sort of data things, and we're not trying to say in all of the stuff that we taught here, dismiss everything you hear. We're not saying like, you're an, Tom, with sort of a talk or whatever, we're just saying this is completely rubbish. I think the idea is sort of levels of probability and trust within what's going on here. So I'm even spoken in the book about anecdotal evidence, and we're saying, well, actually that can be very, very useful if we know how to interpret it and how much trust to sort of put in that. So when we're hearing these talks, we just have to be sort of slightly skeptical. We might think, oh, well, maybe this is sort of got through sampling bias. So I don't want you to sort of come away from this thinking, I can't trust absolutely everything. It's sort of levels of trust in the statistics that we hear.
It's not you're not calling for radicals. You see people say lies, damn lies, and statistics. But one of the quotes we use in the book, which I love, and I think it is a guy from Frederick Mosteller, I think, and it is. While it is easy to lie with statistics, it is even easier to lie without them. So the statistics, yes, they can go wrong in really profound ways, but they are also a lot of the time they're your only way of getting to the truth. And even if a lot of the ones around you are flawed, they are little insights, and you can use them cleverly, and you need to be aware that they aren't flawless. They aren't sort of perfect, clear windows into an unvarnished reality. You need to be just sort of, okay, so this sounds interesting when they tell me that X number of people have died of whatever, but how many people should I expect to die of that number of people? How is it carried out well? Should it just sort of be ready to ask a few questions of it, but rather than say, well, X number of people, that sounds really bad. That, it's a question, exactly as Dave says, levels of trust, and also a willingness to just sort of interrogate where they're coming from and how they're made.
And I think there's two things I guess we would be worried about. One is, we're sort of selling as people are just accepting these willfully, which I'm sure they're not. And the other one is just people refusing to accept it at all. And I think one thing that I often see is that when you see people presented as statistics, they go, oh, that's just rubbish, and then continue thinking what they thought before or whatever, which is probably wrong. The whole idea of statistics is, that this is the best, and if it's done well, it's the best way of representing what we know about the world. And so it is this idea that, if we approach them with this sort of open-eyed willingness to learn from them, then that's kind of the best way, really. And we're only going to do that if we get better at statistics and statistical literacy, which I think brings us on to our stat style guide. Do you want to sell it for us, Tom?
Yeah, I'll try. So the end of the book, the book as a whole is for readers, because there are a lot more readers than there are journalists, and you want to keep your market as big as possible. But the end of the book, we have an 11-point style guide, which is just sort of thing, just for journalists, but and to sort of try and present numbers better in future. So things like, we talked about absolute risk. You present the absolute risk as well as the relative risk, so that people know, so they don't just 18% more likely to have seizures. That sounds bad. 18% more likely than what? And get to do things like make sure that the study you're reporting on is representative of the literature, like we talked about, and not just rather than just say, oh, this week red wine cures you of heart disease or whatever, we're saying, well, what does the sort of as a whole, what does the scientific literature say? And other things like putting numbers in context, so people know when you say 17 people with blue hair have died of pleurisy this week, is that a lot? How many people without blue hair died? Is that what is the background rate? Just ways of putting numbers in context so people can use them to assess their own risk, to navigate the world. That's the thing. Then statistics should be, especially statistics in the media, we navigate the world and the world of risk through the numbers we read, that we hear on the news. And if what the journalist's job should be is to put them into context, to make them as informative as possible, rather than using them as a weapon to bludgeon opponents with, or as what's that quote? To use them as like a drunk uses a lamppost, more for support than illumination. And so what we're trying to do in the statistical style guide is just help journalists, most of whom I think are really well-meaning, generally intelligent, but just often not brilliant with numbers, to just sort of help push to help use these numbers in a more informative way. And I think we'd love it if you happen to read the book, or even if you don't, to go and check out the website howtoreadnumbers.com, which has a copy of the statistical style guide on the end, and just read it and see if you agree with it. And if you do, you can sign our petition to go and see if we can get more outlets, media outlets, newspapers and things to sign up to it, or do their own and just find ways of presenting stats better.
I think that's we would like people to create this own, because different news outlets are going to have different
needs,
levels or things, different needs for their readers, and it'd be fantastic if you guys do it, because although it is for journalists, it can help you too in terms of how you go about reading these things, but it does also start with the readers, because just like from the very, very start quote we had, a spelling error, I'm pretty sure that you'll see many people in the comments, if Tom accidentally sort of uses less rather than fewer, or the other way around, people will tell him, and they will say, look, you've done it wrong, this is that. And it's part about demanding a sort of better level of statistical literacy. And I think if we, the readership, sort of say that, then I think journalists are more likely to follow. So it's all right, we're sort of trying to do a sort of carrot and a stick approach to them, and hopefully we'll solve all the world problems and everything will be better.
Yes, world peace by next year.
Yeah, but I think that's it, and it was I think it was a enjoyable experience for us, and I hope everybody who's watching this enjoys it too. And thanks very much for inviting us, and I hope you watch more of the fantastic program that's available to you all.
Yeah, thanks very much to the Bradford Literature Festival. We really enjoyed it.
Yes, excellent.